Hello, I'm Tim Vanderelli from Ferrocell USA. I'm here today with collaborator Michael Snyder from, oh, sorry, I didn't even start the PowerPoint presentation, thanks. This is my first time doing this. My name, I already told you that. Mike Snyder is a co-researcher, and we published a paper together with Doctors Alberto and Adriana Tufaile from the São Paulo University in Brazil. Unfortunately, they couldn't make this conference. They had other obligations. We're here to talk about controlling light diffraction with magnetic nanostructures. Oh, yeah. I'll get the hang of this. We're presenting the main results of our research using ferrofluids to control the light scattering in some devices based on nanotechnology. We are presenting the Ferrolens, or the Ferrocell, which is commercially known, which is basically a Healy-Shaw cell with ferrofluid, and another device, the Ferrolens cross polarizer, which is a ferrolens placed between two polarizers, obviously, and illuminated with white light and subjected to a magnetic field. We've obtained the equations which represent these systems and solved them analytically and numerically in order to compare with the patterns obtained using the experiments. We've also explored the experiment with the patterns obtained from atmospheric optics, such as the perihelic circle and sundogs, obtaining experimentally in lab the jumping laser dogs and the paralaxic circle, which Dr. Tufaile coined the phrases. And more can be read in our paper, recent paper, Observing Dynamical Systems Using Magneto-Controlled Diffraction. What's a magnetic field and how do we represent it? Well, historically, Michael Faraday recognized the magnetic field line based on his observations of iron filings and compass needles. But we know a magnetic field is in 3D vector space. And what the Ferrolens does is it basically takes a slice of that 3D vector space and shows us in 2D what the, in actually any angle. It doesn't have to be parallel or perpendicular to the field. It can be coming at any angle, and you will get ISO lines showing us that field. This frame here is basically just a better image from the last one. And in this particular image, we see a magnetic pole. This is one pole. I don't know if it's north or south. It wasn't marked. In this image, we have a dipole. We have one pole up here and one pole down here. And we can see the block region between these two. And these images are basically flatter than the ISO, but these are slices from the 3D. In this image by Michael Snyder, we see two magnets side by side. The south poles are in the center. It's lit with a ring of lights similar to this, and the north poles are on either side here. And we see the scattering in these patterns. In picture A, we see a Ferrolens device with lighting without a magnetic field. And here we placed a magnet on it and show the scattering in this. The Ferrolens combines many technologies and disciplines, including magnetism, optics, ferrohydrodynamics, and visualization methods. For example, you can see similar light diffraction in clouds. Ice crystals aligned by the cloud's electric field diffract a beam of light known as crown flashes, and they're guided by the electromagnetic field, as we see in that image. More information can be read in our article our paper from 2017 on light polarization using ferrofluids and magnetic fields, and it includes information about the atmospheric effects of scattering. And at this point, I'm going to turn this over to my colleague Michael Snyder and let him finish up.
Okay. Um, in this slide, we have the Ferrolens cross-polarizer apparatus. This apparatus is designed for education. You can imagine in high school or first-year physics in college. Uh, we have two polarizing films, and we have the Ferrolens in the center with the ferrofluid. And on the B figure, we can see the top of the device. And on C, we can see where you place the magnets for the applied field. Okay, on this slide, we have the real-world image from the cross-polarizer and the applied field. And on the right-hand side, we have the computer simulation of the same applied field with a single light source. And the calculations are done with hyperbolic polynomials. In this slide, in figure A, we have the vector field of a ring magnet that's magnetized through the thickness. In figure B, we have the Ferrocell image of the same ring magnet, and we have LEDs around the perimeter. In the C figure, we have the real-world image of the cross-polarizer with its single light source and the ring magnet. And the D figure, we have the computer simulation of the C figure. And you can see there's high correlation between what the computer says we should be getting and what we're actually getting. And you might wonder, how is this possible? How's all this working? And this is probably the most important slide I have. Ferrofluid is designed to, ferrofluid particles are designed to repel other ferrofluid particles unless you apply applied field, which overcomes that repulsion, and the particles start sticking together. Now, these particles are in a field gradient, so they're moving at the same time that the rods are growing. And what really is happening here is we're self-assembling a diffraction grating. And there's some little magic going on here, because when you remove the field, these particles chains will start dissipating. So when you apply the field, you get a diffraction grating, and when you remove the field, you lose the diffraction grating. These properties, these physical properties of ferrofluid was known even in 1985. Ronald Rosenzweig and ferrohydrodynamics described these as anomalies. And the funny thing is, what was an anomaly, or something we didn't want in 1985, is actually something we really want in 2019, because we have diffraction gratings on demand. Okay, this slide, we're basically just reinforcing the idea that we have a diffraction grating that's being created on demand. We have multiple layers of it, and you can describe this with the geometric theory of diffraction, and it's also related to Kircher dipole transverse scattering. That's another theory that we're checking into. Okay, in this image, we're shooting a green laser into a ferrofluid, into a ferrocell, and using different applied magnetic fields to rotate the diffraction flare, or the wing, sometimes we call it. So basically, the laser has not moved. The only thing that has changed is the applied field, and we can rotate that flare anywhere we want to, 360 degrees. Okay. On the left-hand side is a computer-generated plot of a North Pole and a South Pole of two magnets that's facing the observer. On the right-hand side, we see a real-world image of a Ferrolens with 36 LEDs around the perimeter. And you can easily see that, the left-hand image is a dipole and the right-hand image is also a dipole. In this image, we have 6 magnets total, 3 of them with the North Pole facing the observer, 3 of them with the South Pole facing the observer. And we have computed the isopotential lines and also the vector lines. And you can see that the isopotential lines run side to side. And in the real world image, the same magnets with the lines of scatter or the diffraction pattern that we're seeing run side to side. So we have high correlation between the computed image or the computed plot and the real world image. Okay, this is one of my favorite slides. This magnetic array is a very simple array, but it took me 10 years before I tried it. I've tried probably every other array. And how this array works is the magnetic moment of each magnet is pointed to the midsection of the next magnet. And when we compute the field, we ended up with a twisted star pattern. And when we tried it in real life, we also ended up with a twisted star pattern, showing that both images are showing us isopotential lines. While it's not a perfect match, it is a darn close match. Okay, our conclusions are the light patterns obtained with the Ferrolens depends on the geometry of the light source and the applied field. The cross-polarized light patterns closely resemble the patterns of hyperbolic polynomials as shown in our recent paper. The self-assembled chains of nanoparticles created by the applied field act as a dynamic diffraction grating when the field is applied and disappear when the field is removed. And the light diffracted by the ferrofluid rods seem to follow the isopotential lines of the applied field. And we'll open up the floor for questions.